Hello everyone, my name is Mafalda, I am a PhD student from Portugal, and in this video I will present a poster titled ADAPT-VQE, Impact of Noise, Importance of Symmetries, and Circuit Depth Reduction via Operator Removal. As you probably know, currently available quantum computers suffer from high error rates and are not error corrected. So if we want to make use of them, we should settle for algorithms which employ shallow circuits. Variational quantum algorithms, or VQAs, have gained popularity because they were designed with near-term viability in mind. These algorithms resort to a classical computer to optimize some gate parameters in a quantum circuit, called ansatz. By offloading part of the work onto a classical optimizer, we soften demands placed on the quantum computer and reduce circuit depth. The first VQA is used fixed structure ansatz. One popular option was to build these circuits using problem-agnostic and hardware-efficient layers, but this strategy was shown to induce barren plateaus, a trainability issue which hinders efficiency. Problem-tailored variants have also been developed. An example for the electronic structure problem is the unitary coupled cluster singles and doubles, or UCCSD ansatz. But evidence shows that this ansatz has unnecessary components and is not well defined upon trautorization. The ADAPT-VQE algorithm emerged to tackle these issues. This algorithm essentially breaks the problem-tailored ansatz into pieces to form an operator pool, and then proceeds to create a new circuit from scratch by selecting the most relevant operators one at a time. The selection criterion is taken to be the magnitude of the energy gradient with respect to the variational parameter of each potential operator at point zero, which we can measure in the quantum computer. The poster covers three topics concerning this algorithm. The first one relates to the selection criterion. ADAPT-VQE uses the magnitude of the gradient to choose new operators because this is an interesting indicator of the energy change that an operator might produce, since it quantifies the impact on the energy that it has locally. However, this criterion is not perfect, since the gradient does not give us all the information about the optimization landscape. Before adding an operator, we may not know better, but once we've added it to the ansatz and optimized the parameters, we will know the impact on the energy it actually had, and we can attempt to revisit our decision. Our idea was to develop a protocol to remove operators from the ansatz when their impact on the energy is underwhelming. Since we never know how close to the ground state we are, we judge an operator's performance by comparing it with posteriorly added ones. If the energy impact of a given operator is surpassed by a significant margin by a successor of it, we attempt to remove it and re-optimize the energy. If we verify that the impact on the energy was roughly as low as before, we effectively remove it. An important problem is that it's very likely that the removed operator will be re-added to the ansatz in the iteration immediately after, and once again have a lower impact on the energy than other operators could. But since we know that this operator produced a lower energy change than we would predict based on its gradient, we would like to use that information to make a more informed selection. To tackle this, we introduced a penalty system that lowers the gradient of removed operators by exactly how under average their energy change by unit gradient was. This creates an effective gradient which prevents the algorithm from prematurely re-adding operators to the ansatz. The re-addition only occurs when there is no other operator that will perform better under the assumption that they produce an average energy change per unit gradient norm. We tested our operator removal strategy via numerical simulations and verified that for a 10 operator ansatz, it decreased the error relative to the original protocol to 16% for lithium hydride at 1.5 angstrom and to 3% for hydroxide at the same interatomic distance. The second topic concerns the importance of using fermion-inspired operators. We define different operator pools with growing degrees of similarity with fermionic excitations, and analyze convergence in light of the composition of the state in terms of Slater determinants. We verified that less and lower magnitude determinants with altered particle number and z-spin were associated with a faster convergence. But beyond this, using operators in one-to-one correspondence with fermionic excitations did not bring a clear benefit. To illustrate this, we use the pool that preserved these fermionic quantities, but where each operator could correspond simultaneously to all viable excitations or the excitations acting on a given set of spin orbitals. We tested this for lithium hydride at 1.5 angstrom and H4 at the same interatomic distance, and observed that this pool led ADAPT-VQE to converge as fast or faster than a pool comprised of individual excitations until beyond the chemical accuracy threshold. Finally, our third topic concerns the short requirements of the ADAPT-VQE algorithm relative to static alternatives such as UCCSD-VQE. From a noise-free analysis, it is evident that the dynamic creation of the ansatz implies a measurement overhead, because the gradient of all pool operators need to be measured in each iteration. Additionally, the algorithm implies multiple optimizations, unlike static VQEs which require a single one. However, we should also note that, in general, each optimization in ADAPT-VQE will be lower dimensional than the optimization of the UCCSD ansatz, because the iterative protocol selects only the most relevant operators and the corresponding variational parameters. Intuitively, optimizing an ansatz with more parameters will be harder in general, and we could predict that navigating a higher dimensional optimization landscape will require more and higher precision function evaluations. In fact, we verify that for reaching comparable accuracy in the determination of the ground energy of molecular hydrogen using the Cobailer optimizer, the optimization of the UCCSD ansatz required over 30 times more shots and twice the energy evaluations of the optimization of the final ADAPT-VQE ansatz. We then compare the total shot count required by the two algorithms for molecular hydrogen. This number corresponds to the total number of state preparations, repeated or not, that have to be executed on the quantum computer to reach the final state and energy. This number weighs in the fact that UCCSD-VQE requires more shots per energy evaluation and more energy evaluations per optimization, as well as the fact that ADAPT-VQE requires additional measurements per iteration to obtain the gradients. In addition to implying shallower circuits and a lower number of variational parameters for similar final error, ADAPT-VQE required under 2% the number of shots of UCCSD-VQE throughout the whole execution. So in this example, the fact that sampling noise is better tolerated by ADAPT-VQE allows for a reduction of the total number of shots per observable that compensates for the fact there will be a larger number of observables being measured. This is the content of the poster, which I summarize in 3 sentences. 1. Modifying the ADAPT-VQE algorithm to remove underperforming operators can produce shallower circuits in exchange for a small cost overhead. 2. Symmetry preservation is the key aspect promoting convergence in fermion-inspired pools. And 3. A short count reduction stemming from the compactness of the ADAPT ansatz alleviates the measurement overhead predicted from a noise-free analysis. This is it. Thank you for listening.